Hello everyone. Let's start the class of quantum physics for engineering. My name is Youngdal. Let me use laser pointer. So the course website here in the gel.gis.h.kr is also linked to YouTube channel where you can leave comments, and those comments will be answered in detail. The goal and textbook of this course. Golden rules of science and engineering or any other intellectual area. So those are applicable to any engineering and science studies. We always specify the purpose of your class, devices, talk, papers. When you talk about phenomena, consider principle and underlying mechanisms to understand better. Say no to vague and negative expressions. It means we will try our best to be detailed. Incorporate questions and comments of others. Improve your previous thinking results with time. Most importantly, be detailed with time. Adapt to given results, conditions, and environments. So, at first, we will come up with some scenario postulates, some suggestions, right? And we will check the results with the principles and mathematical equations, whether they are matching with each other. Otherwise, we will adapt to given results. We will try to find something missing and something more detailed, some new parameters. In this way, we will find order instead of chaos. When you talk, write, and discuss. So the purpose of this course is, this course provides a basis for semiconductor physics, quantum confinement, band structure engineering, light matter interaction, and wave mechanical descriptions of electrons, photons, and phonons. Here, asterisk or some star symbol will be explained more in detail here. Okay, so the phonons is explained. This is the carrier. Yeah, phonon is the carrier of heat and not developed very well, which implies the importance of its research. In the future, it will be dealt with when we have enough time and students ask related questions. Otherwise, we'll just focus on electrons and photons. Semiconductor devices such as LEDs, light emitting diodes, laser diodes, and transistors are mostly closely related with quantum physics Nanoscale materials are described based on quantum physics, since the wave properties are revealed better in small scale. And we will consider more in detail about the small scale. Therefore, semiconductors, mostly two-dimensional quantum wells, useful for devices, even though there is one-dimensional and zero-dimensional quantum structures. And novel nanomaterials, such as graphene. Graphene is the new two-dimensional quantum structure. And TMDCs, transitional metal dechalcogenides. And there are many other new materials. BTS is just an example. BTS is a new nanomaterial made of boron, titanium, and sulfur, discussed based on quantum physics. Textbook for this class are Quantum Mechanics, Fundamentals and Applications to Technology by J. Singh. And this is good summary of all quantum mechanical concepts, especially chapter 4 to 6 are good for applications. Nanoscale Energy Transport and Conversion by Gang Chen. This is modernized version of engineering students. Chapter 2 to 3 have especially very good with many intuitive pictures. And good point of this textbook is it is dealing with all the important carriers. I mean electrons, photons, and phonons, all based on quantum mechanics. Most of the previous quantum mechanical classes were mostly based on electrons only. But nowadays, electrons are fully investigated, fully utilized for devices already. So what we are missing is actually phonons, which are the heat carriers, or the integration of all different kinds of carriers. For such new purpose, this textbook is actually very useful. There are some other recommended references. For example, 송희성 양자역학. This is actually written in Korean. It is all around mathematical descriptions which are easy to follow. Advanced reference could be wave mechanics applied to semiconductor heterostructures by G. Bastard. The author developed the variational method for calculating wave functions in electrical devices. So this textbook, this is the reference for the variational method. Variational method is the standard for calculating wave functions of electrons. So it is actually very important. Another advanced reference could be the physics of low-dimensional semiconductors by J. H. Davis. Dimensionality is discussed very well. Double asterisk is about the prerequisite. Nothing specific as long as you can solve differential equations. So to follow this class, you need to have some mathematical skills. It is okay even though you didn't take courses on electromagnetisms or phonons, some semiconductor devices. Yeah, still it's okay as long as you can solve some mathematical equations, and most importantly differential equations. But refer to Appendix A of J. Singh and Chapter 1 of Gang Chen for basics if you are not familiar with basics. Before we deal with the Schrödinger equation. Course schedule. So the first week we are here at this point. Class overview today. Physics of waves. Yeah, not Wednesday actually. This is wrong. From next Monday, we will start discussing waves. So wave nature of matter. It will be based on the Gang Chen chapter 2. Then Schrödinger equation based on Gang Chen chapter 2. This textbook is available in library. Even though you don't have the textbook, in the meantime, it will be still okay. I mean, the teaching materials will be good enough to follow the details. But I, suggest you rather purchase this textbook because it will be very useful for your future research works. I think this textbook shows the future of any engineering. Okay, because it is not just simply about quantum mechanics. It is about integration of different kinds of devices. Actually, J. Singh is just the same with any other quantum mechanics textbooks, but it will just focus on applications. So it's a good summary of quantum mechanics concepts. That's good, but J. Singh won't go into details of mathematical development. That's the weakness, I think. So we will consider particle quantum basic problem of any quantum mechanics class, and then particle periodic potential, then harmonic oscillator. These are just the basics of any quantum mechanics course. And then tunneling, spherical potential, and then symmetries and conservation laws. These are related with the angular momentum description of quantum mechanics. And then time-independent approximations to solve some complicated problems. And then for the applications, variational method will be discussed. And then if we have enough time, we'll survey some contemporary application examples in quantum materials. Grading. Homework. A problem set and recommended textbook reading will be assigned. And the deadline for the problem set homework will be the Wednesday of the following week, and it is assigned. There will be midterm and final exams. Grading will be based on homework 30%, midterm exam 30%, final exam 30%, and questions 10%. And these questions explained here more in detail. You can leave comments on my YouTube channel, and I will make with the like button. I will notify the good question with like button, then count the it means it will be counted as good question. That will add to your question points. Okay. Well, bad behavior in the classroom is considered as no attendance. Well, it won't be applied in this course, in this online course, so ignore this part. Moore's law and quantum physics. Moore's law, empirical rule which predicts that the number of components per chip doubles every 18 to 24 months. I'd better use the pen here. So number of components, most importantly the transistor. You can consider transistor per chip. Chip means when you grow semiconductor devices. I said grow. We really grow the devices actually. So the size of the chip is usually like this, on the order of 2 inch. So we call it wafer. Within this 2 inch wafer, we fabricate transistors. Okay. Let's say this square is a single transistor. We fabricate many transistors within this 2 inch wafer. That's what I mean by the number of components per chip. And they doubled every 18 to 24 months. Moore's law turned out to be valid for more than 30 years, but now saturated in the case of silicon. The limit of Moore's law is the transistor with a hydrogen atom size, because we cannot make a transistor with a scale smaller than hydrogen atom size. So this figure shows the number of transistors per chip as a function of time. So we're already around here. So this is 2018 from 1971. So the number of the chips were increasing, and the scatter point, the number of transistors per chip, and we have the linear fitting here. It was increasing like almost like 2 times every 2 years, and then recently it has been saturated. So as the Moore's law it can be called as empirical law, right? It is not based on any intuitive pictures or scientific reasonings. It is just the phenomena, right? Just the experience. So it is empirical law. It is reaching its limit of a hydrogen atom. Hydrogen atom limit is this one. Okay. So the nanotechnology and or faster materials. It means now we are in small scale, so our understanding should be based on some mathematical descriptions and intuitive pictures suitable for small scale, and that is represented by nanotechnology. And we rather consider new materials instead of silicon, especially faster materials. Here, faster materials means the electron speed is faster in different materials. So some alternatives to silicon have emerged as one of the most important areas both in scientific research and engineering. This is an example. This is an article from New York Times on September 26, 2015. The title is Smaller, Faster, Cheaper, Over. It means we tried to make the transistor smaller. If it is smaller, then the speed becomes faster. The operation speed becomes faster. And if it becomes cheaper, even though it is faster, it can be cheaper because the scale is small. So we are using the less materials, less resources. That's why it could be cheaper, but not anymore. So what could be the future of computer chips? So I recommend you read through this article. So it can be easily Googled by yourselves. But the article is not discussing the alternatives very carefully, I think. I mean, it is very good one actually. At this point, 2015, the article deals with the how we can make the smaller scale devices, like new UV lithography techniques. Surely we should pursue such a smaller fabrication skills, something called lithography, by using deep UV. Deep UV means you are using very small wavelength light to fabricate semiconductor chips. If it is not familiar with you, still it is okay. There's no problem. You can simply read through this article. But actually, at this point, the bigger, scale alternatives could be cloud computing. So not just using single computer, but we connect. As we all are very familiar with, right? Data center is the key for our future, as everybody knows, right? And then the silicon could be replaced by some other faster materials such as graphene, or computer algorithm could be replaced like quantum computing. So we note that now people are using multiple cores instead of single chip, single core, and then different computers are connected since single CPU capacity is not good enough anymore, saturated already. And alternatives could be cloud computing. So this is the era connection and fusion. Then nanotechnology, use different algorithm. Important number here could be the electron speed in silicon or any other basic semiconductors. It is 10 to the 7 centimeter per sec. That is the C over 1000. C is the light velocity. In graphene, however, electron speed can be faster, C over 300. Okay. Now the era of new nanomaterials which are governed by quantum physics. Especially the graphene is the two-dimensional materials. Two-dimensional, it means electrons are moving around in two dimensions. So, for example, we can say XY plane. Electrons are moving around here, not around here. Yeah. Now the era of new nanomaterials. There are two research papers exemplified here. One is quasi-ballistic carbon nanotube array transistors with current density exceeding silicon and gallium arsenide. The other is single layer MOS2 transistors. So you can note that basically they are using new materials. So here carbon nanotube, and then here MOS2. MOS2 is a kind of transition metal, decalcogenides, and they are both using the materials, using those materials as channel layers, okay, between source and drain, Applied bias between source and drain will accelerate the electrons, okay, and these electrons will go through some scatterings, okay. So within this channel there could be some defect. The meaning of defect, you can check it out yourself. This is one of the very important research topics. And phonons. Phonons are the vibrations of atoms. And these are also the heat carriers. Another very important research topics. And also, carriers could be scattered off of some other carriers, such as electrons. If there are no scattering sources, or the scale is very small compared to the scattering length is usually called as mean free path, and you will see this many times in the research papers. Mean free path. Without such scattering, we can call it ballistic. So either you try to be without scattering, or you can increase the speed of electrons, okay, in the channel layer. Even though it is considered to be rather old, 2016 and 2011, still many similar topics are being studied, even now. Another approach is the heat. Okay. Here, the figure shows the carrier drift velocity versus electric field. This is very important figure in any semiconductor studies. You can see that drift velocity, drift is the mechanism of carrier acceleration due to the electric field application. Here we are seeing gallium arsenide, germanium, and silicon. And their carrier drift velocities are all increasing with electric field and then saturated around here. Okay. The point here is around like 2 by 10 to the 3 volt per centimeter. So volt per centimeter. So 2 kilovolt per centimeter. So this is the important value. Okay, so any materials will go through some saturation around here. This electric field is actually considered to be very small because when you have a battery like 1.5 volt and it is applied into your devices, and your device scale is very small these days, on the order of 100 nanometer or smaller. And this is the electric field magnitude, and you can easily see that 100, then 10 to the 2, nano, 10 to the minus 9, meter, 10 to the 2 centimeter. So you will see that will be replaced by volt centimeter unit. Then it will be 1.5 by, look at this, 10 to the 2 minus 9, 2, so it will be 10 to the minus 5, so it will be 10 to the 5. So with this battery, single battery, you will generate very high electric field already in your quantum or nanostructure. So what you are doing is you are generating very high electric field, but actually your carrier velocity is already saturated, fully saturated, and your electric field is around like here. Okay, you apply electric field here, and carrier velocity is already saturated. So what we are doing is the extra electric field will generate extra energy of electrons. What I mean by extra energy is, okay, this is the band diagram, conduction band and valence band, and you are generating carriers like much above the band gap. What it means, these electrons will relax down to low energy state. Holes will relax down to low energy state to emit the heat waste energy. Okay, and can we simply remove this heat? No, it's not. It's very hard to remove. So the heat is accumulated in the devices. Surely we are using the heat sink, right? But it is not that efficient from our experience, because your CPU can be cooled down in such a short time. No, it's not. sometimes it takes a very long time, like 1 minute, for example. If we think about it, 1 minute is such a long time compared to the CPU speed. It is faster than gigahertz. Gigahertz means the 1 nanosecond. How about heat removal? It takes a long time compared to that. It is because lots of heat carriers are accumulated in your devices. So the application of such extra electric field is actually inefficient. The reason for this saturation is because of electron phonon scattering. When you always generate extra energy, then you'll generate phonons. The energy relaxation of electron means it will generate phonons, lattice vibration or atomic vibrations. And those atomic vibrations will generate scatterings of electrons. That's why the drift velocity is saturated. Then can we just simply remove the phonons? No, it is very difficult, and it wasn't studied very well because scientists have been so focused on electrons and photons, not phonons. So you'll easily see that it will be extremely hard to find any good textbook dealing with phonons. Okay, so even the very basics about phonons still we don't know. Still, the big problem is the heat actually. So how about just simply remove the heat? It means we have less scattering source. The electron speed will be increased. That's the another approach. But it is easier said than done. Heat removal isn't that easy at all. And it is closely related with something called phononics. Yeah, new science and engineering area emerging in this regard. There is almost no phononics expert in Korea actually. It is mostly focused on, we are most focused on electrons here. Our school is very good for photonics, right? Photons. Still, yeah, we are good enough. But as for phonons, not much. I'm working on phonons even though I have been working on electrons and photons previously. And our group found it is much harder than any other carriers to study. Okay, more details are found in slide 14. Yeah, let me go back to rather easier topic. Actually, quantum mechanics is not that easy, but at least dealing with electrons and photons is much easier than dealing with phonons or heat. Here, the most important example of quantum physics is quantum well. Silicon ball radius is 5 nanometer. What we mean by ball radius is the size of electronic wave function. Okay. Yeah, you will see more details in later coursework. We are approaching quantum limit. Quantum physics are becoming more important in silicon-based semiconductor. Yeah, I already repeated too many times. So in the case of silicon, 5 nanometer is sort of criterion where we should apply quantum mechanics. So basically, semiconductor nanostructures is a good example of quantum well when their size, when their scales approaching 5 nanometer. Here, quantum well means we attach two different materials. In semiconductor studies, materials. I'm writing down materials. Firstly, defined by their band gap. Okay, band gap. Here, different materials I mean by different band gap materials. So the band gap here, material A and material B, material C, they have different band gap Eg. And then different band gap is aligned, and smaller band gap material works as, let me erase a little bit. Okay, that might be better. Let me use the laser pointer here. Material A, material B, material C, they have different band gap. Different band gap means also band gap you are supposed to know, so check it out. Google the meaning of band gap. Basically, there's a band called as conduction band and valence band. The meaning of valence band and conduction band is actually very important. So basically, valence band means the band where electrons are fully filled. And conduction band is a band where the electrons are not fully filled. But those definitions are all at the lowest temperatures. For example, the almost zero temperature, so that carriers are not thermally activated. Those are basic concepts of the bands. Their separation is the band gap. And A, B, and C, they are aligned with each other. Then conduction band and valence band should be connected somehow. And there is offset, conduction band offset and valence band offset. Their offset ratio is also important material parameters for semiconductor studies. But it depends. It is really depending on different kinds of materials. So we cannot simply define here, okay? But there exists some band offset. So, and smaller banding material will become quantum L. Larger banding material will become barrier. Barrier. Okay. So original band gap of this quantum material is this one actually. But once you have quantum structures, then original band gap will be increased like this because of quantum confinement. So there is new energy level like this one for conduction band and like this one for valence band. Electron and hole should be located here, not here anymore. Okay, not here anymore. Once you have quantum confinement, that's when you have quantum L. So this L, quantum L length, is smaller than de Broglie wavelength here. The meaning of de Broglie wavelength will be discussed later on, but here de Broglie wavelength will be replaced by Bohr radius for semiconductor studies, so they have similar meaning for now. So when the scale is smaller than that, then you will have such quantum confinement. Practically, meaning that the electronic energy level is increasing. Okay. Yeah, so quantum engineering of band structures through the control of band gap, effective mass, delta E, separation between different N levels. So depending on the scale L, everything will be changing. So original material band gap will be modified depending on the scale. Okay. Yeah, wave nature of electrons, photovoltaics. So this is the fundamental picture of photovoltaics. Here you are seeing the energy versus wave vector diagram. It is called a dispersion. So we have conduction band and valence band, and their separation is band gap. And this band structure is changing as a function of wave vector k when there is incident photon with certain energy h bar omega, and this energy is converted into electron energy. So the energy separation between this electron and vacant state of electron, which is called as Hall state, is h bar omega. The energy should be the same, then we can say that energy is conserved. And when this electron and hole are excited and they are separated in space, this is not space, this is not real space, this is actually K space. When they are separated in real space, then voltage is generated. That's the way we can have photovoltaics. So the light is replaced by photocurrent. Basic idea of semiconductor lightings. Same dispersion diagram, and we excite electron and holes by using external bias, external voltage application. And then as time goes on, electron and hole recombine to generate photons. In this case, the band gap energy should be the same with photon energy, h bar omega. So the band gap will determine the wavelength of emitting photons. In this case, external voltage is replaced by light. That's the idea of LED, and LED lighting now with 2 nanometer scale active layer. Yeah, actually we are using LED bulbs these days, and the core structure is actually on the order of 2 nanometer. So this figure shows the luminescence efficiency as a function of time. And 1965, 2010, the luminescence efficiency is almost saturated already, and we are using the white light. In old days we only had the red light because it is easier to generate. In that case we used gallium arsenide phosphide then gallium phosphide, zinc doped with oxygen, gallium arsenide phosphide doped with nitrogen, and then aluminum gallium arsenide, aluminum indium gallium phosphide. Here slash means quantum structure. Usually first one is quantum well, next one is usually barriers or opposite. So we are separating quantum well and barrier structure. Sometimes it is, the order is, opposite. And then recently people are using indium gallium nitride structure. Okay, so indium gallium nitride becomes quantum well, this becomes barrier. Surely barrier has larger band gap, quantum well has smaller band gap. This indium gallium nitride can generate green and blue. Quite recently it can even generate red light. And then mix them up, we can generate white color. Quantum size effect changes colors. Novel nanostructures. Examples on zinc oxide nanorod. It is one-dimensional structure. So on the substrate, it is grown like this way, one-dimensional. So carriers move around like along this axis, like g-axis, but not around xy axis. There could be nanotubes, zinc oxide and gallium nitride nanotubes. Nanotube means in this nanostructure there are holes like this, okay? And also quantum dots. So the scale is on the order of 5 nanometer in this case. This is an example of quantum dots. Cadmium selenide, cadmium telluride is very conventionally available quantum dots. Those quantum dots in some liquid, their size is changing, and then their colors are changing. You can think of what kind of size could be corresponding to what kind of colors. So small size generate larger energy, it is corresponding blues, and larger size of quantum dots match with smaller energy, then red color. Phonon is nowadays a key for quantum world. Well, it is because it has not been studied very well compared to electrons and photons. Just like any other carriers, phonons have wavelengths and frequency. Okay? As we all know of the wavelengths lambda, frequency mu, and we multiply them, then it becomes speed. Okay? Speed of here phonons. We have alright, so we have different kinds of phonons: infrasound, sound is on the order of like kilohertz, right? And then ultrasound on the order of megahertz. Hypersound on the order of gigahertz. Heat, terahertz. Here I'm talking about the frequency of phonons, not the photons, okay? So this is different topics. The applications of infrasound, for example, sonar, to detect the distance within ocean, and the music, depending on sound technology, on the order of kilohertz. Ultrasound, medical imaging we are using. Hypersound, wireless communication we are using. And there comes heat. Still we are working on it, or this is important research area. Some new research topics could be phonon diode. Just like electric diodes, we want to control the direction of flow of phonons. Okay? Clocking means if there are some phonon waves, the phonon wave propagation dynamics is modulated so that if there is certain object or structures, we just bypass of that depending on certain structure designs. Especially people use phononic crystals. Sometimes we call it metastructures. So within certain original material, it could be any materials. It could be silicons, it could be gallium arsenide, it could be graphene, and then we have some fabrication techniques so that some holes, so vacant area, and there is material vacant, and then there comes material. They are repeated, so the original dispersion means energy and K relation will be modified. There comes topic of phonon laser recently. It is not photon laser, it's different topic, phonon laser. So we select certain frequency component of phonons and then amplify. Physics for device, electronic dispersion. Silicon. Here energy K diagram is expanded. So we are seeing different bands. Conduction band is not actually just the same. The conduction band, minimum point of conduction band could be varied at different K point. The minimum point is called as belly. In semiconductors, there's something called gamma valley, L valley, X valley. In the case of silicon, the minimum point of conduction band and maximum point of valence band is not matching at the same K point. It is located at different K point. Then electrons will be relaxed down to the lowest energy point, indicated by yellow shade here. Holes will be located into the minimum energy point indicated by yellow shade here. So the different K point will be related with optical transition. The electron here, hole here, if they recombine, it means electron relax down to lower state. In semiconductor studies, people usually say that electron and holes are recombining. But photons with energy h bar omega usually has extremely small momentum. So that electron hole recombination to happen, their momentum should be very, very small, almost zero in this energy K diagram or dispersion. So the electron hole recombination should be happening together with additional process of phonons. So phonons can have various K values. Okay. So photonic emission should be happening only for vertical transition here, almost K equals 0 point. And this silicon is called as indirect gap semiconductor, and they are not optically active because electron and hole, they are separated in this different K point, so that they should be involved with phononic emissions or phononic absorptions. Think about it. If there's electron and if there's a hole here, the electron should give its momentum like this one, K0, to phonon. So phonon should be generated first to remove this momentum. And phonon has its own energy. So the original energy point will be slightly lowered down by the amount of phonon energy. And then this electron, phonon emission will reduce to the 0 point, and the electron can recombine with the hole. So it is quite complicated process now, and this complicated process has very low efficiency. That's why optically inactive. On the other hand, gallium arsenide has direct band gap structure where electron and hole, the minimum and maximum point occurring at the same K point. Then it has very strong optical transition because optical transition is now allowed. It is called a direct gap semiconductor. Chart for device studies. What do we need for R&D, research and development? Basically, we need quantum mechanics, most importantly Schrödinger equation. Then we can have understanding on the electronic structure, wave functions, optical properties. Other than that, we need to have electromagnetism represented by Maxwell equations, based on which we can understand optical fields waveguides, propagation. We also need to know the kinetic theory to understand the electronic dynamics, because there are not just single electrons, there are many electrons. So we need to consider the distribution of electrons. Then you need to know Boltzmann equation. Here important topics are KVL distribution, potential profiles, scattering, KVL, the current densities, and also for device operations we need to know IV curve, optical output, efficiency, also CV curve is very important, capacitance, voltage curves. And in this class we will only focus on this quantum mechanics part. Okay, that's it for today.